previous lecture, and I have just a quick review today. So you have seen how sin elimination takes place. This is the other aspect, anti-elimination. Which functional group undergo anti-elimination? Good living group that you have already come across, like diazonium, like acetate, or you have come across in aliphatics, nucleophilic substitution reactions. The good living groups like tosylate, you have come across brosylate, nosylate, triflate, nonoflate, etc. All of them are good living groups. So these good living groups, other than the specified, you have come across, other than xanthates, other than uh, xanthates, you have come across triamine oxides, you have come across. Similarly, you have come across sulfoxides and selenooxides. All of these functional group undergo syn eliminations, whereas all other good living groups, functional groups, are in fact undergoing anti-eliminations. And anti-elimination shall always need a base, but syn elimination doesn't need a base. You have seen in previous, you see here, no base is being used. Here we are not using any base. These reagents are used to synthesize sulfoxide or selenooxides. So this X may be sulfur, X may be selenium, and then this is being oxidized. Ozone is acting as an oxidizing agent, which is oxidizing sulfur or selenium in fact, generating this entity. So here this is the other resonance form of 2 generating likewise. So you see here, there is 7-member transition state, hydrogen 1, 2, 3, 4, 5. This is 5-member transition state. And in case of xanthate, this is 6-member transition state. Again, there is no base we are using here. Sodium hydroxide, which is used here, is to synthesize xanthates. Then this should be neutralized to achieve these xanthates. Once xanthates you have in hand, then it is not going to be used any base. Base is present within the molecule. So similarly, you have seen in this case, you have seen nitrogen and nitrogen oxide or triamine oxides, etc. They are not involved any base. Base is present within the molecule. So in case of syn elimination, you don't need any base. And syn is concerted, very similar. Anti is also concerted mechanism. So both are E2. E2 means elimination by molecular. The reaction in which the base and the substrate undergo side by side. So in this case, anti-elimination is also concerted. It also takes place in a single step. Here I am going to present, let's say this is erythro. So in this case, you can see both ethyl group and methyl, longest carbon chain is on vertical position, and like substituents are on same side. So this is a erythro entity. Now erythro is, I have presented that erythro here as a front carbon. This is the front carbon, this is the rear carbon. So front and rear carbon are presented in, this is a Fischer projection, this is a Newman projection in fact. So if this group undergo anti-elimination, then we should have this group and the other group opposite to each other. What we have done here, I have missed here, we are going to react this primary amine with HNO2. HNO2 is a, if you remember, this is a nitrous acid commonly called, not nitric acid. Nitric acid is HNO3. This is HNO2, synthesized by the reaction of sodium nitrite, NaNO2 with HCl. So this results in the formation of NaCl and HNO2. This HNO2 is highly reactive. It reacts with primary amines. Primary amines react with HNO2 and form diazonium, nitrogen-nitrogen triple bond. One nitrogen is already present, which is this nitrogen. The other nitrogen is coming from HNO2, right? So it generates a triple bond with nitrogen, nitrogen triple bond. Now, if this group leave nitrogen with positive charge, if it takes this electron pair off to stabilize positive charge on nitrogen, it shall eliminate in the form of N2. So N2 mean nitrogen molecule. This is very stable. In air, nitrogen is present 76%. 76% in air is in fact 78%, not 76. 78% in air is nitrogen N2. So it eliminates very stable entity in leaves the molecule because this is the gas. So this is a good living group, best living group even called. So this hydrogen is living in this way. So we need a base here. If we are taking a base, is taking this proton off. So because this is sterically hindered when we are having this group present at this position, this is sterically corroded. But on the other hand, if both living groups are opposite, if we are having this group present at this position, we are having this position, this living group, and you see this hydrogen, the base which is picking up this proton. I haven't presented here base because a few slides later I shall explain which bases we use for eliminations. So this hydrogen shall leave without electron pair and this leaving group shall leave with electron pair from two different adjacent carbon atoms. And because both leaving groups are, you see, they are 180-degree to each other, totally opposite to each other. So that's why this is anti-elimination. And because they are eclipsing each other, so this is a thin elimination. Thin elimination forming a more sterically corroded position because here not only these two substituents are involved, but also a base shall approach here and base is typically around it. So that's why it shall not approach very easily to this position. In previous you have come across, there is no base required. These two are not eclipsing, these two are at 60-degree to each other. In this case I have presented these two living groups are sterically crowded, no doubt, but no base is required here. So that's why syn elimination is easily possible. But in these substrate, when we have a base is required, so that base picks up this proton, so it becomes more sterically crowded position. That's why it doesn't follow this one, or you can say the reaction rate with this is extraordinarily slow. But reaction rate with this elimination, when nuclear base is picking up proton from this position, leaving group is 180-degree to that, so steric crowding is zero. So this is a much more stable conformer rather this one. If you compare 2 versus 4, this conformer is less stable, this conformer is more stable. That's why this isomer shall be generated in more concentration as compared with this one. So this is one I have presented. So anti-elimination is resulting a E isomer. Group of highest preference is ethyl here, phenyl here. They are opposite to each other, so it is E isomer. But if we are focusing on this one, this is a 3O isomer. You see, same isomer, but both hydrogens are this group configuration is opposite. Front carbon is same, but rear carbon is a change in configuration. So when it is undergoing leaving, you see this is front carbon is same, rear carbon is changed. This is the same. We have reacted with HNO2 resulting loss of HNO2 from here. HNO2 reacting with this nitrogen forming a diazonium. This diazonium is a good living group. Leaving hydrogen from here within the presence of a base make this position sterically more crowded. So this isomer which is generated as a thin product is not dominating one. Now look at the other possibility. In this case, this hydrogen reacting with a base is not sterically crowded, and similarly this is not sterically crowded. So both living groups are living in opposite direction. So one is living with electron pair, other is living without electron pair, resulting in the formation of a isomer in which top priority ethyl on front carbon and phenyl on rear carbon are top priority. Both of them are together, eclipsing each, mean they are cis to each other. So this is a Z isomer. So in this case, if you are starting with trio, you end with a Z isomer. If you are starting with a retro, you are ending with E isomers. So E isomer is dominating in this case in retro. In trio, Z is dominating. We are not saying only Z is forming when we are using trio, or E is forming only when we are using retro. We are saying they are dominating over the other isomers. Mean other is also formed. So what groups we should have here? Not only this, because I have presented diazonium is the best living group. What are other groups can be? It may be halogens, chlorine, bromine, iodine. All right. It may be other groups that you have already come across, like acetates, like tosylate, bromylate, nosilate, triflate, nonaflate, etc. All of these groups that you have come across, good living groups in aliphatic nucleophilic substitution reaction, all applies here. They always undergo anti-eliminations. But very specific functional group you have seen: triamine oxides, xanthates, sulfoxide, seleno oxides, etc. They basically undergo clean elimination only. Rest of the all other undergo anti-elimination. Any group which shall undergo anti-elimination shall require a base. So a base is required for them. So in this case, you can see the base is very poor. We are not having much base present in this case. So in anti-elimination, you have seen there is no base present in. So here we are not having a base present in syn elimination, but in anti-elimination we need a base. Base always reacts here. So I have not presented base here because I have presented base that we use for elimination reaction in next slide, a few next slides. Is it clear to everybody? E2 elimination, it may be syn and it may be anti. Right, so proceeding further, E1 elimination mechanism. E1 is very similar. You have come across SN1 mechanism. Just like SN1 mechanism involve the generation of a carbocation, very similar happens in this case. Let's see if I am going to present this. E1 also compete with SN1. Let's see, we have a good living group present at this position. So rather it undergo concerted mechanism. Concerted mechanism means this group leaves with electron pair and hydrogen leaves without electron pair in a single step. Concerted mechanism, which is E2 elimination. Either they are eliminating in syn way or anti way. So that follow E2 elimination. But here, if they are not going to and eliminating syn or anti, but it is going stepwise mechanism. Mean one group with electron pair leaves first, so it leaves first, generating a carbocation here. This is a slow reaction rate. So it is generating a pi orbital here. You see, this X leaves generate a positive charge here. So this pi orbital is here with positive charge. All right. Now, if hydrogen is here, then base can pick up in a next step to pick up this proton from here. This proton shall leave without electron pair, generating a double bond here. If it is unchanged, let's say this configuration is unchanged, then we shall get the same isomer just like we get in E2 elimination. This is presented R1 and R3 are eclipsing, R1 and R3 is eclipsing. This one, this isomer shall be generated. But let's say because free rotation is there, if it rotates, this R4 shall approach here, R3 shall go there. In that case, if hydrogen leaves, then it shall result this isomer. Because there are equal opportunities, free carbon-carbon rotation here, so it can generate this isomer and that isomer in equal ratio. So I haven't defined in this case what is the substrate. These R1, R2, R3, and R4 are. So anyhow, in this case, both two isomers are possible. These are trends, E or Z. Both shall be formed in equal ratio. Like two stereoisomers are being generated. If this base is a poor base, then it can act as a nucleophile. If it act at a nucleophile, it can approach from this side, it can approach from this side, resulting to stereoisomer, which is a substitution product. So that can compete with this by having, in fact, these two entities. Base is not a good base, but it is a good nucleophile. So if it is a good nucleophile, then this reaction doesn't take place. Now, how we can justify this? How we can get this change if we are using an extraordinary good base? We shall see in next few slides which base we normally use. All right. So DBU, DBN, DMAP, etc. we normally use. So what is their structure and how they work? We shall see later. We are supposed to use a good base. If we are using a good base and we are going this reaction at high temperature, then keeping in mind elimination shall be favored as presented in this arrow. So this reaction is taking place at high temperature with a very good base. We shall see a few slides later. So in that case, this base shall pick up this proton. It is protonated, leave this molecule generating a double bond. Now two isomers are possible here. So 3 and 4 both shall be formed equally. Just similar, you get two enantiomers form in equal ratio in E in S and 1 substitution reactions. So because this is very close to that, SN1 proceeds stepwise. More than one steps are involved. E2 proceeds in single step. The same is happening here. E2 proceeds in a single step. E1 proceeds in two steps. First step is slow, second is fast rate. So here is an example I am going to present. That let's see, this is a tertiary carbon sulfur. Now if we react this, this is a thioether. Thioether can react with thiazolide. It is a good nucleophile. So it shall substitute this iodine by sulfur. So sulfur is making a bond with methyl, and this iodine bond breaking this SN2 reaction, resulting in the formation of sulfur. Because sulfur attracted one bonding electron pair, it obtain a positive charge here. No, it is making a good living. Now this leaves this molecule in this dimethyl, or you can say dimethyl thioether. It leaves, and we shall get a positive charge here. This positive charge is the tertiary carbocation. This tertiary carbocation can also be generated by another method. Let's say if we don't have this functional group present, say we have chloride, bromide, or iodide here. If we react with silver ion, if you remember, silver ions have a very high affinity with halide ions. So the silver ion may coordinates with this chloride, bromide, or iodide, agitate this bond, polarizes this bond. As a result, this Cl leaves with electron pair forming silver chloride precipitates, silver bromide, or silver iodide precipitate. Their colors are different. Silver chloride are white in color. Silver iodide are bright yellow in color, commonly called that is basically just looking like an appear, but commonly called amber color, which is dark yellow color, thick yellow color. And if it is silver bromide, it forms light yellow, just like lemon color, lime yellow color, light yellow color it produces. So this is a procedure how we can two different substrates. This is a substrate number 5. This is substrate number 8. They are two different, having same alkyl group but different functional group. So we can generate same carbocation. All right. Now this carbocation is when let's we react this with water. Now water can act as a nucleophile. Water is not a very strong good nucleophile. It can act as a base as well. It can pick up a proton from this carbon, from this carbon, from that carbon. Now if it is two possibilities, because water is not a good base, water is not a good nucleophile as well. So it proceeds very interesting products, two different products in fact. If we are using a substrate, in fact, let's say we are using, in this case, two products are possible. If it is acting as a base, it shall pick up a proton from here, generating a double bond here, which is this one. Second, if it is acting as a nucleophile, it can approach this orbital, generating this product. This is a substitution product. This is elimination product. Now, this is product number 9. This is product number 10. If it is synthesized by this route, it produces 63% 9 mean elimination product, 36% 10 mean substitution product. If we are proceeding this mechanism like this one, so in this case 9 and 10 approximately have same ratio. You see here ratio 63.7 and 36.3. Here it is 64.3 and 35.7. They are very close to each other. So it means because they are generating same intermediate. If you remember, SN1 reaction proceed with generation of a intermediate. This is an intermediate. First substrate, no base is produced. Slow rated step generate have only substrate present, no base. If we double the concentration of it, shall be zero order. This is why it is called even eliminations. So this is generating, in fact, what we are getting in this case is, in this case, you have come across, we have generated this entity in this case, which is the number 2 isomer. It is being generated, which is in fact a intermediate. Then intermediate reacting with another reactant base to generate the product. So here both isomer, either this intermediate is generated from substrate 8 or it is generated from substrate 5. In both cases, whenever it is reacted with water, it forms both two products at same temperature. All right. So here temperature is room temperature, it is recorded. But if we increase the temperature, so definitely this product number 9 shall increase, its percentage shall increase and this shall decrease. If we decrease the temperature to room temperature mean 25 degrees Celsius, then the substitution product shall start increasing and this shall start decreasing. So this is approximately 2:1 ratio. So elimination is double than the substitution product. This is what we meant for E1 elimination. We differ from E2 in mechanism. So in E2 elimination, both living groups, one living with electron pair, other living without electron pair, live in a single cell, that is called unaltered state. In E1 elimination, different take less one breaks the proton and creates a olefin. Is this clear to everybody? Hello.
Yes, sir.
All right.
Sir, आपकी आवाज कट रही
So
है.
this is the mechanism involved in E1 eliminations, right? So E1 substrate, what previously observed from group, but
सर
as
आपकी
we know,
आवाज नहीं आ रही.
if let's say Is everybody there listening me?
Yes, sir.
Alright, so there was a disconnection. I don't know why. Anyway, I'm sharing it again. Is slide number 11 visible?
Yes, sir.
Alright. So we have approach to this even elimination. Just you see, if this carbon is tertiary carbon, then this tertiary carbocation shall be very stable. It shall follow even elimination. But if this is not, then it shall not follow this. So I have presented this in next slide about this. Let's see. So in this slide, you see this is the same substrate, a tertiary carbon, simple tertiary carbon. So I'm just focusing on E1 substrates, the nature of substrate. If it is a very simple substrate, mean X group, living group is attached to a very simple tertiary carbon, then it shall generate a tertiary carbocation. Tertiary carbocation shall react with a base very similar like this. This is a tertiary carbocation reacting with a base, resulting in the formation of olefin, which is this one. So this is very simple. But let's say if there is a structural change present in the substrate, let's say this is a gold living group. This side we have an alkyl group. This carbon is not a tertiary carbon. You see, this carbon was a tertiary carbon, but this carbon is attached with two carbons. It is not a tertiary carbon, but a secondary carbon. If it is secondary, then E1 and E2 can compete. But here, keeping in mind, we have a carbon-carbon double bond, and olefin is attached to this carbon, where living group is present. So what it shall form, this carbocation, if you remember, this carbocation is resonance stabilized. I have presented the other resonance form here. So when it is resonance stabilized, so this group is more stable. So definitely this carbocation is more stable. This resonance form shall be more stable. This is secondary and this is primary. Primary is less stable, secondary is more stable. So this is more present in this form. So now a hydrogen from this can be removed in the presence of a base. Very similar, like you have the second step you have come across in previous mechanism. You have carbocation generated base picking up a proton from next carbon, one proton from next carbon, resulting in the formation of olefin. So it is picking up a hydrogen from here, the base, and generating a double bond. This double bond I presented in a red is generated due to the elimination. This double bond is already present. So you see a secondary carbon is preferring E1 mechanism rather E2. Why? Because there is a change in the substrate. Carbon is secondary, but next group attached to this is an olefin, which is stabilizing the positive charge by resonance. Here it is stabilized by hyperconjugation. Hyperconjugation produces less stability, whereas resonance generates more stability. All right. So this is the difference in fact. Now just focus on this substrate number 3. This is very similar to this part. This is very same. This is secondary carbon. But here rather olefin we have an aromatic system. If we have this aromatic system, now you can see if this group leaves, we generate a positive charge here. This positive charge shall be resonance stabilized by all these three double bonds. Five resonance forms shall be possible. I have just presented two resonance forms here. Now you can generate another resonance form here, another resonance form here, positive charge here, then it shall be back here with the positive charge there. So five resonance forms are possible. So it has more resonance form possible. This is more stable carbocation. This is less stable carbocation. This is least stable among these three. So in that case, when it is this one, so one hydrogen shall leave from it, generating a double bond here that I have presented with a in red color. This red double bond is generated due to elimination. All right, just take another change. Let's see, this X is a gold living group, but this Y next to this is electron donating. It has an electron, non-bonding electron pair present on this. This may be OH, it may be alkoxy group. This may be SH, it may be SR group, it may be dialkyl amino group. If it is nitrogen, it shall have only one non-bonding electron pair present. If it is sulfur, it shall have two non-bonding. Oxygen shall also have two non-bonding electron pairs present at this position. So if there is this group leaves, this is again secondary carbon, less stable, but generates a positive charge here, which is resonance stabilized by this non-bonding electron pair. This Y may be oxygen, sulfur, nitrogen, phosphorus, etc. So if it is stabilizing this positive charge, it shall generate a positive charge here. These have two resonance form only. These also have two resonance form. So they have almost equal stability. But here positive charge in both cases is on carbon. Here positive charge is on carbon, other is on heteroatom. This shall have less percentage. It shall have more percentage. So in this case, this hydrogen shall leave from here, generating a double bond at this position in the presence of base, generating this double bond likewise. So these are dependent upon a secondary carbon can also undergo even elimination if it is following such protocol. A secondary carbon can follow E1 mechanism if it is closer to an olefinic double bond, aromatic system. Now, keeping in mind this aromatic shouldn't be carbocycle only, it may be heterocycle as well. All right, or maybe a heteroatom is attached to the same carbon where a living group is living. So this is the different substrates, although they are secondary carbon but undergoes E1 eliminations. This is what I have would like to present here, that it one factor of E1 versus E2 is the nature of the substrate. All right, is this clear? So I think we have just 2 or 2.5 minutes remaining. So I shall prefer, if you have any question regarding this, then we shall focus basis required for elimination, and then we focus another mechanism in solution phase is E1CB mechanism, and then similarly in gas phase elimination, EI elimination we shall focus, and then I shall focus on application in next lecture.